All right, so finally we get to conditional probability models. We've had a good setup so far. The objects we're going to predict are going to be distributions, yes, but we're going to restrict them to be elements of parametric distribution families. And so it'll be sufficient to just produce the parameter corresponding to the distribution that we want to predict. Now, conditional probability models are very general. Today, we'll start with the general, we'll continue with our general setup, but pretty quickly we're going to specialize to linear probability models. But we will generalize it very easily to nonlinear methods in a few weeks when we cover nonlinear methods. So you can attach the same reasoning that we're doing on linear models today to gradient boosting models and neural network models in a few weeks when we come to those. We should close the door. Thanks, Kevin. OK. OK. So first I need to make a quick disclaimer. So most of what we're talking about today will be linear probability models. And there's something very related we may have heard of called generalized linear models. So generalized linear models are, in some sense, a special case of what we're talking about today. And it's when you look for implementations in Python or R or wherever on some library for the types of things we're talking about today, your best search term is probably generalized linear models. The reason we are not doing a formal development of generalized linear models is because it's a bit heavy. There's a lot of kind of terminology and technical information. It's very interesting, but I think it takes us a little bit off course, development of exponential families and these sorts of things. And we don't lose anything, as far as I can tell, for practical purposes. So there are theorems you can state for generalized linear models that we're not going to be able to state here, but we don't need these theorems in our work. One advantage of generalized linear models is that they're restricted enough that implementations are fairly uniform across everything in a generalized linear model, whereas ours is a bit more general. And so if you wanted to take advantage of that generality, you'd have to have special implementations for lots of different cases. So I just want you to be aware of we're not properly doing generalized linear models, but that would be a special case of this. And I'll point you to some terminologies that generalized linear models use that we can't actually use because we're not in that context. So I'll just point out those discrepancies. So we'll talk about generalized regression, which it's not the most common term, but I think conditional distribution estimation is standard. And the setting is a rehash. Given x, we're predicting a probability distribution of y given x. And just some examples that are kind of named models that fall into this framework: logistic regression, probit regression, Poisson regression, linear regression, generalized linear models, as I said, and then all those are linear, and then generalized additive models, which we mentioned in answer to a question earlier this year. We may or may not cover that, but gradient boosting machines. I didn't even put down here because I don't think it has a name, but neural networks when you're producing a probability distribution of this from parametric class. So all these are instances of conditional distribution estimation. So let's start with the simplest, Bernoulli regression. So the Bernoulli regression problem. We get an input x. We want to predict the distribution over two possibilities. And we'll represent the two possibilities as 0 and 1. It's more common. We were using -1 and 1 earlier in the term. 0 and 1 is more common in this probabilistic framework. So that is what we'll go with. So we want to predict the distribution on 0, 1. How can we define such a distribution? It's pretty straightforward. There's not a lot of choices. It's the Bernoulli distribution, and the Bernoulli has a parameter, theta, which we can define to be the probability that y is equal to 1, okay, given x. So Bernoulli theta will be a way to refer to the distribution on 0, 1 that has probability theta of 1. And of course, the probability of 0 is 1 minus theta. Great. So we're predicting a probability distribution on 0, 1, which we're representing by the Bernoulli parameter theta, which is between 0 and 1. So we essentially have to map somehow from RD, our input space x, to a number between 0 and 1. All right. So we do this in 2 steps in this linear method. In the first step, we are extracting information from x and summarizing it in a single number. And that extraction is a linear mapping. So that's why this is called a linear method. So x gets mapped to some w transpose x. W transpose x should remind you of the score function we had in classification, right? It's not the number we're trying to end up with, but it's a number we get on the way. And as usual, we can pack x with an extra kind of a constant feature if we want to have an affine function of x be our score, so to speak. And so this gives us a number this gives us a real number, because the output of a linear function of x and rd is going to be some real, but it's not constrained in any way. So we're going to have to be able to map a real down the 0 to 1 interval. So any suggestions on how you might do that? Say again? Yeah, so you're suggesting a way to map W transpose X to 0 or 1, but we need to map it into a probability, which is something in the interval between 0 and 1. So we want to be able to estimate probabilities and not just hard classifications. So we need some kind of a function that maps us from reals to 0, 1. And it's going to be we'll call this a transfer function. And so we introduce a new function f that takes as input our score, W transpose X, and returns theta, the parameter we're actually trying to produce, which is between 0 and 1. So we need some function that maps any real number to something between 0 and 1. And we have some flexibility on what we choose there. But once we have that function, the full kind of conditional probability model takes as input x and produces f of W transpose X. So all the information in x gets mapped down to a number, W transpose X, and that gets piped through a transfer function f, which takes this potentially arbitrary real number and maps it to be between 0 and 1. Now, whether it's doing anything useful or not, OK, that's too soon to say. That'll come in our fitting procedure. But here's the main terminology alert I wanted to give you, is that in the generalized linear models context, which this certainly includes, this function f would be called a response function. It's also called the inverse link function sometimes. The link function would typically map from theta back to W transpose X. OK. Great. So here's 2 commonly used transfer functions. This would be also fitting into the GLM framework, so you can call it an inverse link function or response function as well. So 2 functions are here. One's called the logistic function, and one is the familiar normal cumulative density function for the normal distribution. And you see they both have an input domain. They extend for the entire real line. And the output range goes from 0 to 1, which is what we like. And the shape of this is an S shape. These are called sigmoid functions because of that shape. It turns out when we go through the whole procedure, when we have the full kind of end-to-end model description, what will result by using this logistic function will be, in fact, logistic regression. And we didn't talk about it much, but we had logistic regression in lecture 3 when we talked about classification losses. The loss function there in that empirical risk minimization framework gives you the same prediction function that the framework we're developing here will give when we choose this logistic regression, the logistic function as our transfer function. Probit, the normal CDF, will give rise to something different, a little bit different, called probit regression. And you could imagine there are other transfer functions as well that can be used here. How do you choose among them? I think we're going to give the standard machine learning answer here, which is you can see which works better on some holdout data. Okay. So this describes the set of prediction functions that we're considering. You see my terminology is gradually morphing into like hypothesis space, the set of prediction functions that we will choose from. And how do we do the choosing, the learning? So let's just rehearse our spaces. Input space RD, output space 0, 1, the two classes. The action space is, in some sense, the distributions on 0, 1, which we're representing just by the probability of 1. So the action space is the interval 0, 1. Is that clear? Yeah. And the hypothesis space, the set of things we might choose to predict, are going to be functions that map from x to f of w transpose x. And then the only thing undetermined is w. Right? Once we have this parameter vector w that determines the mapping from x to our score, and then the function f is fixed, which maps our score to something in 0, 1, which is our probability. All right. So we can choose the w using maximum likelihood. And let's look what that looks like. Let's develop it ourselves. So suppose we have a few x's. I won't give specific values for, well, why not? Why not? Let's suppose x is reals, right? So some possible inputs, -3, 0, 1, 2, right? What are y's? What's possible y values?
0.
Good.
0.
Good.
1.
Thank you.
1.
I'm going to go 0. OK. All right. Prediction function. We are now looking to, so our general strategy is let's see how to evaluate one prediction function for an arbitrary w, and then we can just search over w's. So prediction function would be of the form, let's use, OK, so use an arbitrary f here. F of w transpose x. But give me a possible value for w in this for this problem, just to be concrete. What type of value would w be for this problem? It would be a real number, because x is a real. So let's consider w equals 1. All right. And let's develop some scores. So w transpose x, that's just 1 times x. Let's make it 2. That's a little bit boring. Let's go 2. Right, 2. OK, so this would be -6, 0, 2, 4. Right? So those are our score functions. And now we need to get our likelihoods. In this case, it's also probabilities. So that would be f of w transpose x. F of w transpose x is what exactly? What does that represent here? Be right back. Got it? Remember what it is? OK, so y is 0 for this observation. What probability are we assigning to the outcome y equals 0? OK, let's do one step at a time. So in this entry, f of w transpose x, that's going to be f of -6, f of 0, f of 2, f of 4. All right, for likelihood, we need to determine the probability of y under the prediction. So I'm going to write p of y here. All right? P hat for the predicted probability. All right? So how can I express p hat of y for y is 0? There's a convention that we agreed on, which was that so our parameter that we're predicting is theta, and that was going to be given to us by f w transpose x. And what we agreed on is that, where I told you, and you guys had to follow along, that theta was going to be the probability of a 1. So probability that y equals 1 is what theta is. Clear? All right, so back over here, p hat of y. So what is y? Y is 0. So I need the probability of 0 given we know what f of negative 6 is. So?
1 minus theta?
Yeah, right. So theta is the probability of y is 1. We want the probability of what actually happened, which is y is 0. So this should be 1 minus theta. But what's our estimate for theta?
F.
At f, right. Or in particular, for this input x, it's f of negative 6. Exactly. So 1 minus f of negative 6. That's our predicted probability for what actually occurred. That is our likelihood for the observation y equals 0 given x is negative 3. All right. Let's do another one. What's the p hat of this y? Y is 0. Say again? 1 minus f of 0, exactly. OK, how about this one? Y is 1 given x is 1. What's our predicted? F of 2, right. So y is 1, so the probability of y is 1 is theta, or f of 2, right? Great. And this one, the last one?
1 minus f4.
Yes, 1 minus f of 4. OK. So we know the probabilities of all the outcomes. So if this whole thing is our data set, what's the likelihood of our data set? So data, so likelihood of this model, let's just say w equals 2, because that specifies the model. Once we know w, everything is set. Likelihood of w equals 2 for the data is basically, could write as p hat of the data. You know, what's our assigned likelihood for the data, probability of the data, and then what is it?
Product of all.
Yeah, it's the product of all these things. It's the product. I'll write it down in 2 steps. So it's p hat of, OK. Let's index these examples. 1, 2, 3, 4. So this will be x1. This will be y1. So it's the probability of 0 given x equals negative 3 times the probability of 0 given x equals 0 times probability. And all these are p hats, our estimates. And then, yes, as you said, this is exactly the product of these, of this column. So 1 minus f of negative 6, dot, 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 1 minus f of 4. OK? So this whole calculation, that's for w equals 2. If we go back through and write this out for a generic w, that's easy. This f of negative 6, that reverts to being w times negative 3. This is w times 0, w times 1. So we can write this likelihood in a very generic form. Okay. In terms of w. But there's one very clever way to write these terms, which seems to be useful often, and in this case in particular, which is using the power. That's right. So let's see if we can get this right. So each of these terms is either going to be 1 minus f of something or f of something, right? And which it is depends on the value of y, right? So generically, it's going to be so this is the probability for y equals 0. And then this is the probability for y equals 1, right? So say we're talking about a specific example, x sub I. So we can raise this to a power that is yi. So yi is either 0 or 1. So if we raise something to the first power, you just get the value back. If you raise it to the 0th power, you get 1 back. So you could imagine there's a way to put yi into the exponents of these things so that what do we want to happen? We want when yi is 1, we want to get this piece. When yi is 0, we want to get this piece. So what do I need to put into the exponents to get that to happen? Where do you want 1 minus yi to go? All right, let's try that. If we put 1 minus yi here, when yi is 0, then this exponent is 1. And so, yes, we get this back. And then what does that mean for over here? Put yi here. So again, if yi is 0, this piece is 1. So this drops out, and we're left with just this piece. And if y is 1, this piece drops out, and we're left with just this piece. So this is kind of our clever way to write this term in the likelihood. So the full likelihood, then, the probability for a data set D is going to be equal to the product over our data set I is 1 to n of this. This would be our likelihood for an arbitrary w. Now, this is something we can work with. We can take the logarithm of it. Things simplify nicely. Then we could differentiate with respect to w. Then we can optimize over w. Any questions on that? And then we'll stare at the slide that repeats that same thing. OK. All right. So this, in the end, is the expression we get for the log likelihood for our estimate determined by w, for an estimate determined by w for a data set D. And then we would like to find the maximum of this expression over w. And we can do that using some optimization techniques. This one does not have a closed form solution. So we can use some iterative methods, stochastic gradient descent. So kind of as a potential homework problem would be to find the SGD step directions for logistic regression, which is with one of the link functions, or probit regression, which is the other link function. And these are things that are fairly straightforward to derive. And that's what would be going on behind the scenes if you did logistic regression or probit regression in a statistics package. All right. So that's Bernoulli regression. Any questions on that? And this kind of sets the tone for how we're going to do the rest. So the rest of the lecture, we're going to go through several examples like this to get very comfortable with this routine of, because you should be able to come up with these models yourself. The idea is that you pick a probability distribution, parametric distribution that you think is well suited for your task, and then you can find your own mapping from some linear score function to the parameter space of that distribution. So let's try it for Poisson. So in Poisson, we'll again take our input space to be RD, and then our action space, as we've been discussing all day, are these counts, 0, 1, 2, 3, on to infinity. And we're going to produce the parameter, the lambda parameter, the mean parameter for Poisson. That's the goal we're trying to output. So lambda is non-negative because it's the mean of some counts. So we need to produce something in the interval 0 to infinity. That's our action space. And so we are looking for, we want Poisson regression is linear regression. So is a linear probabilistic model, I should say. So x is first mapped to some score, W transpose x. And we want to map that to lambda. And lambda is between 0 and infinity. So what might we be able to use as a transfer function that takes us from reals to non-negative reals? Say again?
Modulus, acceleration.
OK, you could use modulus or absolute value. yet that certainly maps us in the right way. Another possibility is exponential. Exponential is the more common one. That's what's used in Poisson regression. Typically it's referred to in Poisson regression. And so that's what we'll do here. So yes, f of w transpose x will be e to the w transpose x, which of course is always non-negative. And so it's a good fit for the Poisson parameter. That's the form of the Poisson regression. Now we can turn the crank to figure out how to find the optimal w. So we're looking for an expression that gives the likelihood for some data for a particular w. And then we will maximize over w to get the maximum likelihood. That would be our recipe. So this works out a little bit more simply even than Bernoulli. You don't need that exponent trick. You just write down the log likelihood, which we already had in the previous module. And so here's the theme. Here's a step that will be recurring. You first write down the form of the density or probability mass function on your output space. That would be this. And the parameter will show up. And the key step, so this is so far just estimating a distribution. But the key step to make this a conditional probability model is, remember, we are predicting the parameter of the distribution. So everywhere we see a parameter lambda, we swap that out with a f of w transpose x. So f of w transpose x, that is our prediction for the parameter lambda. So we take the form of our distribution on our output space y, and we replace each lambda, each parameter value, with our prediction for it, which for Poisson will be e to the w transpose x. So now there's no more lambda here. Now what things depend on is w. W determines the mapping from x all the way to the parameter lambda. We can work it out, and you can maximize this expression with respect to w. Okay. Turns out it's concave. It's straightforward to optimize. And there you have maximum likelihood for Poisson. Any questions on Poisson? So this is essentially, this is what is happening. We could use this for taxicabs somehow. We'd have to find a way to encode time and or space as an x. Okay. I don't know if this is the best way to do the taxicab, but this would apply in the same situation, that we're trying to map from some input covariates to a Poisson distribution.
Can we go back to the previous one? It's the same question, but the logistic one, right? Sure. How is the relation? So eventually this will provide W. Yeah. Given the X, this optimization will create, produce W. Right?
Yes. This optimization will produce a W.
Is this related to the two-class binary classification?
How is the W related to the two-class binary classification problem?
We talk about the classification.
Yes.
And this one is producing given an x, it will produce a distribution.
Yes, given an x, this will produce a distribution on what space? On the space of classes, 0 and 1.
It will give a distribution of the classes.
Yes. So end-to-end, Bernoulli regression, it takes as input an x, and it produces a number, but not just any number. This number is between 0 and 1 and is interpreted as the probability of class 1. So this is a theta. We should interpret this as theta, which is the probability of class 1.
In the classification, we try to tag it with 0 or 1 here. And that needs one additional step to do.
Oh, if we want to actually produce a hard classification, that's a great question. So this prediction function produces a distribution on classes. And I claim that that should be all you need for any downstream task you could possibly want. So maybe if you want to produce a hard classification, the typical thing you could do a threshold, but once you have the probability distribution, you could ask to produce the most likely class. Would be one way to do a hard.
You need, but you need to pick a specific one to do, right?
Right. So for binary classification,
it corresponds to what threshold in that case? For the previous one, we talked about the binary, right? And this one will create a distribution. But to cast that distribution into a binary decision, you need one additional parameter.
yeah. So the point is that if you want to do a hard classification, produces 0 and 1, you need some way to go from a probability predicted to an actual classification. Absolutely correct. One way to do it is to threshold. If you choose that way, that introduces an additional parameter. And you could use techniques we talked about 2 weeks ago on things like precision and recall. And there might be different trade-offs on how you want to choose your class based on a threshold. Yeah. It becomes less obvious when you have multiple classes. And I think it's most common to just choose the class that's most likely. The most likely class in a binary situation would correspond to a threshold of 1/2. All right. So the similar question you could ask for Poisson regression. Now we have a distribution over all non-negative, all integers from 0 to infinity. If you wanted to produce a single number, how would you do it? And there's different ways you could approach it. But my claim is that once you have the distribution, any loss function you could imagine to assess the single point prediction can be optimized with respect to the distribution function that you are predicting. All right. So we're set on, yeah, question?
So it's not really, I mean, when we say logistic regression, it's not really regression per se. Like you can use, I mean, you're regressing between 0 and 1, but you're using that to classify.
So the question is, why is this called regression, logistic regression? I don't have a good answer for that, unfortunately. I was thinking about that maybe it's because as an intermediate step, you have a real valued number. Maybe there's some historical reasons that go beyond my understanding of how these naming conventions came about. All right, let's do a couple more. Let's do conditional Gaussian regression, which is interesting. It turns out to be quite simple. So let's consider the case: input space RD, output space reals, and let's suppose we're going to predict a Gaussian distribution, mu sigma squared, but let's, for simplicity, assume sigma squared is known. All right. So the only thing we need to produce is a mu, the mean of some Gaussian. So in that case, we can represent the distribution just by the mean, a real number. Our action space is a real number. And so when we do our linear score function W transpose X, we already have a real number, which is the domain we need for the parameter mu. So our transfer function could be just the identity, because W transpose X is already in the space that we need it to be in. So we don't need to have f be anything interesting. We could just have f of x equals x, which is what we'll take for now, the identity link function, or inverse link function. And now what happens when we write down the likelihood for a given W for a set of data? You look up your density of a Gaussian distribution and you plug it in, and we don't need to work through the details, but you end up with this expression. So this is the log likelihood of some data for a particular W, where the mapping is I get an x, I look at W transpose x, and that is directly the mean of the Gaussian distribution I'm predicting, because we don't need any additional mapping. W transpose x is already a real value, has the right thing. So let's just stare at this for a moment and think about what would happen when we maximize over W. And the thing to note is that a lot of this stuff is irrelevant. If we're maximizing over W, this term is independent of W, so we can drop that. We're maximizing this negative expression. Well, that would be equivalent to minimizing it without the negative. This 2 sigma squared is independent of W and can pull out. You could drop it without changing the optimizing value. And what you're left with is exactly the square loss, the empirical risk for square loss on a linear hypothesis space. There's no 1 over n here, but that's the only difference from what we've had before, the most basic case. So, well, we know how to solve this. We have many ways to solve this. But this draws one connection between so square loss you can view as a way to produce Gaussian distributions with uniform variance everywhere, and you're predicting the mean of some Gaussian distribution. That's just another interpretation of what's happening with linear regression. All right. Let's do one more. This one is very important and a little bit different, multinomial logistic regression. So this will give us our first method in the course so far to handle multiclass, more than 2 classes. So let's see how that will go. So let's suppose our classes are, we have k classes, 1 through k. And we're producing a distribution on k classes. And I think the formal term for that is categorical distribution, a distribution on k discrete elements. I've also heard multi-Newly as an analog of Bernoulli. In any case, how are we going to represent a categorical distribution? There's different ways to do it. If we have k classes, let's do it with a vector of k elements. Each entry in the vector gives you the probability of the k possible classes. So we're looking for theta 1 through theta k for the k classes, and they need to sum to 1 and be non-negative. Okay. And so if we want to figure out the probability of a given y under that distribution, we just look at theta sub y, where y is a class label. Y is something 1 to k. Is that clear? All right. So we are going to need to start with x, and we're going to map it into some space from which we need to get this vector theta 1 through theta k. And whereas for Bernoulli regression and all the methods we've talked about so far, we've mapped our x into a single number, now what we're going to do is map it into a vector of k numbers. All right? So rather than w, looking for a single w, you could think of it as looking for kW's. 1 w for each of these thetas. So that's what I've written here. X maps to this k inner products. We have each of these w's is a vector itself. Don't be confused. This is not like the entry of a vector w. Each w sub I is a vector of what dimension would it be? Just to make sure we're all aligned. Of dimension d, because we always take x to be rd. That's right. Good. So each of these w's is itself a vector. So how many kind of one-dimensional parameters are we trying to estimate here? D times k, because we have d times k numbers to estimate. D in each of the w's, and there's k of those. So we have this vector now representing each x, and the entries of those vectors are not quite good enough for our distribution because they don't necessarily sum to 1, and they're not necessarily non-negative. So we need a function, a transfer function, to map from some arbitrary vector now in Rk into a proper probability distribution on k elements. And that's where the softmax function comes in. You might have heard of softmax. So softmax, it's a mapping from Rk to Rk. So its input is a k-dimensional vector, its output is a k-dimensional vector. But what it does is it recasts them so that every entry is greater than 0 and sums to 1. Let's verify, first of all, that each of these is greater than 0. So the exp of anything is greater than 0. We're summing some. So yes, every piece of these are non-negative. And then do we see that when you add those together, we get 1? Pretty trivially. Because we have the exact same sum in the denominator as we'll get in the numerator. Great. So the output of the softmax function, whatever the input vector is is going to be a representation of a distribution on k elements, like k classes. So it will give us a categorical distribution, no matter where we end up from our linear score vector now. All right. And then we can just turn the crank. This gives us a way to evaluate the likelihood of any given data point. And we, again, look to maximize the likelihood. So what exactly are we predicting? This is the type of object this is what we use to do a prediction. So if we get an x, so for any pair x and y, we want to, for given x and a particular y, we can compute the probability of that y predicted for the given x by this formula. So if we want to predict the probability of y equals 1 for a given x, we take w sub 1. We compute the score for class 1 with w sub 1 transpose x. And then this expression gives us the corresponding probability for that class. So to compute the probability distribution on possible class labels, we would have to run this computation for each y. So we'd run this k times, and we get the distribution on the class label.
So the Bernoulli case is a special case of this.
Bernoulli case is kind of a special case of this.
What I mean is the summation is 1, so it looks like you have one additional, you don't really need the k.
Yeah, that's right. So we're a little bit over-parameterized in the sense that all the thetas always sum to 1, so could we just have used k minus 1 thetas and know that eventually it has to sum to 1. So the simplest way would be we need non-negative thetas that sum to less or equal to 1, and we'll have k minus 1 of them, and then we know the kth one is the remaining probability mass, would be one way to do it. So that's essentially what we're doing with logistic regression, where we only have a single theta for logistic regression. We say theta is the probability of class 1, and then we know that the probability of class 0 is 1 minus that. So here we've explicitly captured each theta, and yes, there's some redundancy, but this is a convenient way to do it. But yeah, sometimes it's some people like to do it with kind of k minus 1 instead of k. That's true. So this might be over-parameterized, but I'm never so worried about that because we're going to regularize later, and so these things become less of a concern. So those are the examples I wanted to run through. Any questions? Because the last step, I'm just going to wrap up by tying this back to our empirical risk minimization framework. Shall we? OK. So maximum likelihood as empirical risk minimization. So what were the ingredients for our statistical learning theory setup? A lot of it's the same as here. We have an input space X, we have the outcome space Y, we have the action space, and then we have the loss function L, which takes an action and an outcome and gives us a real. Right? And then our most basic way to, we have one more piece, hypothesis space, right? The hypothesis space. Hypothesis space is a set of functions mapping from input space to action space. Right? And the machine learning problem is we need to find a function in our hypothesis space that does well with respect to the loss. And our most basic method for that was empirical risk minimization. So ERM was, let's find the argmin over the functions f in a hypothesis space of the average loss on some data, right? And the loss is between the action, which is f of x, and y. Okay, this is empirical risk minimization. And so now let's write down maximum likelihood framework here. So the maximum likelihood was, so we're predicting like for every x, we predict a p hat y. I'll do p hat sub x. So for every x, we have a different probability distribution on y that we're predicting, right? And the log likelihood was the sum, 1 to n, of the log so for every xi, we have a predicted distribution on yi. That's p hat xi. And to get the actual likelihood of the observed yi, we just plug it into that PDF or PMF that we produced. Is that clear? So maybe the best way to write this is, for any x, we produce a probability distribution function, probability mass function, which is itself a function. The output, the action space, you could think of it as a function itself, that when you plug in values, it returns the probability or the likelihood. So that's what we've done here. For every xi, we've got this p hat xi. We've plugged in yi, taken the log, and then we're summing. And this is the log likelihood, which I'll write L of p hat for some data d. So the question is, can we write this in this framework? So we need a loss function. That's the thing. So to be, the loss function has to map what type of elements? What are we looking for here? So I'll write it down generically first. The loss function takes an action, and it takes an outcome, and it gives us a real. What's our action space in this world? Say again?
Probability distribution.
Indeed. Our action space is probability distributions on y. That's right. Let's write down a probability distribution on y as p. All right, little p. That's what we've been using. We've been writing p hat, actually. Let's write p hat. So this p hat, it's not a number. It's a function that gives you back the likelihood of something in your outcome space. That's right. And what type of thing is y? That's something in our output space. So I'll just write y for that. So the loss function takes a p hat and a y, and what's it map that to?
A real between 0 and 1.
Yeah, it's, well, does it? So what we're kind of looking for is to put this term, this log, into something like this loss function. So is this log of the log of likelihood between 0 and 1? Not really. The likelihood would be, if this were probability, it would be between 0 and 1. And then, OK.
So a negative number.
Perhaps, but not always. OK. So so is this a loss function of this form? Let me write this a little differently. this is a funny thing, but this is also what it is. So p hat of xi, this is a mapping from xi to a distribution on y. So what we're doing is p hat of xi gives us a probability, let's just say probability density function for simplicity. It could be a mass function. And we're evaluating the observation yi on that. All right? So we want this to be large or small? We want this to be large because we want to maximize the likelihood. We want loss functions to be small. So in some sense, the loss function should be the negative of this. So let's write this down. Yeah, right on the next board here. So let's take the loss to be negative log, and then the likelihood of what we observe, which is going to be log of okay. So this piece, p hat xi, that's what's being plugged into the loss function. So let me write it this way instead. All right, so this is the loss function that we're plugging into. Let's summarize. The loss function takes an action, which is a probability distribution on y, and it takes an outcome, which is y. And it evaluates the log of the likelihood assigned to the outcome y under the predicted probability p hat. Right? So our system produced, let's fix x, we got x. Our system produced a predicted probability distribution, p hat. An actual outcome occurred, y. We need to score how well does p hat do in regard to the actual outcome y. We need a loss function that takes the predicted probability distribution, p hat, and the actual outcome y and gives us a score. And that's what this is doing. It's evaluating p hat at the observation that actually occurred. That's p hat y. So this is the likelihood of the outcome assigned by our predicted probability distribution. And then we take the log. That's the log likelihood of the outcome. And then we negate it to get it in the right direction, because we want to. A loss should be small to be good. So that's why we negate this. So this is then in the form of an empirical. This is now an empirical risk, can be interpreted as an empirical risk minimization, where although we want to maximize this, if we negate it, then the piece in here can be interpreted as the loss on our predicted action and the actual outcome. It takes some time to digest. This function yielding a function is a little odd, but that's what we need to do if we want to map it back to our empirical risk formulation. This, by the way, is why I don't require losses to be non-negative. Some developments ask for loss functions to be 0 or larger, but then it leaves out the possibility of having this kind of negative log likelihood loss. So, all right. And the slides just cover what we had here. Any last questions before we wrap up? Well, one way to think about it is you believe your data has certain shape, and then you're doing what's optimal for that data under that assumption. I prefer a different approach, which is that, and it ends up the same, but it's just a different way to think about it. So one way to think about it is that let's assume our data is generated in this way. It's Gaussian, it has sigma squared, variance, et cetera. Another way to think about it is that the data may have a very complicated distribution. I don't know what it is, but I need to find a hypothesis space that's simple enough to not overfit. I need to choose a set of things I'm going to predict. And I will start by predicting something very simple. I'm going to predict a Gaussian with variance sigma squared fixed, and I will learn to predict the mean using some linear function of x. And that's my hypothesis space of possible things. And I can try that, and I can see how it works on validation data. And then I could say, all right, let's try another hypothesis space. Let's try a different sigma squared. Let's try nonlinear functions of x. Let's try to learn sigma squared also. And you can make more and more complicated sets of kind of conditional distribution functions that you're willing to predict. This is kind of more, this kind of makes it less of a assumption about the world and more of a hypothesis space choice and a model selection problem. I feel that fits in better with our machine learning view of the world.
If we want to do regularization, what do we do?
Great. So if you want to do some regularization, what do you do? So it turns out that the very natural way to do this is to use Bayesian statistics, which we're going to talk about next week. And what it amounts to is putting a distribution on W. So right now we are finding the best W. In Bayesian approach, we put a distribution on W and find the W that's most likely given the data. So we'll talk about that next week. And that amounts to regularization. Yeah?
So when we have the expression for likelihood, the product of all the probabilities, when we go from a discrete distribution to a continuous distribution, do we use the PDF or the CDF in that product?
OK, good question. So at the very beginning, I restricted us to predicting distributions that were either represented by PDFs, so densities, or PMFs, probability mass functions. And you need to have one of those two things to talk about a likelihood, which is the evaluation of one of those functions at the data point. So we're using one of those two, PDF or PMF. If we're in a situation where Y, the output space, outcome space, is discrete, it better be a PMF. If it's continuous, a PDF.
So for your city problem, like how did you find out the underlying distribution? Was it?
So for the city sense problem, how do we figure out the underlying distribution? You mean Poisson or negative binomial or these sorts of things? Yeah, so that's a model selection problem. So we know that Poisson is the simplest and negative binomial is a generalization. I mean, if you look at the data, you can see that Poisson is called underdispersed, where the variance is too small for the data. This is especially true for the Penn Station problem. And negative binomial lets you have variance determined by a parameter. So that suggested itself.